Hello everyone. This is an opportunity to look under the cover of a quantum lab. I will show you a common day with a graphene-based quantum impedance standard at CMI within a GIQS project. You will see typical steps that are necessary for application of graphene device in a resistance metrology. Then, CMI's fully digital bridge will be used for direct realization of capacitance unit from AC quantum Hall effect. The story begins with delivery of the device. We have received graphene sample in the overpressurized container. Such system is used by CRIS and PTB to protect devices against its contamination during the shipment. The container is filled with an inert gas. The device is mounted to conductive plate, so there is a protection against an electrostatic charge. Removing the device from the container is simple and straightforward. Installation of the device to the cryoprobe is simple too. We use a cryoprobe VSM-12 that was developed at CMI for realization of both DC and AC measurements of the quantum Hall effect. When the device is mounted and covered with a protective shield, it is time to dip the cryoprobe into the cryostat. The cryostat is cooled down with liquid helium in advance, so the cryoprobe has to be immersed slowly for prevention of the device against any heating shocks. Such procedure is similar for both graphene and classical devices. Now, it's a time to perform first characterization of the cooled device. Contact resistance, Rx6, longitudinal resistance and Hall resistance are checked prior any metrological application of the quantum Hall resistor. Parameters of the device are measured during sweep of the magnet field. An additional resistance measurement at room temperature before cooling can be performed too. A current source and a high-resolution multimeter is usually used for measurements during the magnet field sweep. When position of the well-quantized plateau is identified, the device is prepared for high-accuracy measurements with cryogenic current comparator. In the next step, operation conditions of the cryogenic comparator are settled and we can start with evaluation of the device quantization in DC regime. For example, the device shown here is well quantized in the field of about 4 Tesla. Okay, now we are finished with DC characterization. It's time to move to AC measurements. Let's start with reconnection of the cryoprobe from CCC to AC digital bridge. The digital bridge is designed for operation in a fully digital and digitally assisted mode. So both impedance ratio scaling and RC linkage are possible. For full characterization of the device in AC regime, a plateau shape, a longitudinal resistance measurement with modified bridge, and a current dependency has to be checked. We plan to use this device for demonstration of RC linkage, and it seems that it is quite well quantized at around frequency of 1 kHz. So, we can move to RC measurements. We will perform direct comparison of a capacitor against AC QHR at frequency of 1233 Hz. We will use a 10 nanofarad capacitance standard. Let's stabilize it in an air bath and simply connect it to the bridge. A 1-to-1 impedance ratio measurement is performed in the fully digital mode. With the bridge stability on the 10⁻⁸ level, it is easy to perform forward and reversal measurements. The value of the capacitance is evaluated from von Klitzing constant and bridge voltages. Afterwards, a fresh 10 nanofarad value can be applied for calibration purposes. And that's all! After finish of the measurement, the cryoprobe with graphene device is heated up. The device is disconnected from the probe and placed back to the container. The container is washed up with an inertial gas and closed for later use. Thank you for your attention. In the case that you have survived watching this video, I am quite sure that you will survive application of the graphene-based devices in your lab too.